So next we will be seeing an example of insertion. Assume that we are trying to insert the elements 5, 15, 2, 25 and 3 in this order. So if you are providing the elements in some order, first element will be the root. So we will be having 5 as root. We will be having 5 as root. Next we will be inserting 15. 15 is greater than 5. So we will be inserting it as a right child. 15. Next we will be inserting 2. 2 is less than 5. So we will be inserting as a left child. Next we have 25. So we will be moving right. 25 is greater than 15. So 25. So we will be placing it here. Next we will be inserting 3. So we move left, then we need to move right since 3 is greater than 2. So we will be having a tree like this. So if you do some traversal, say in order traversal, we have already seen in order traversal. The order is in order traversal, the order is left, root, right. So in all these traversal, we will be starting from root. So we will be doing a left, root, right. So we will be moving here. We will be having left, root, right, no left. So left, then printing root, then right, that is 3. So left subtree is finished. Next we will be printing left root. Root is 5. Then you need to move right. Since there are elements left, you need to again follow left, root, right. No left, then root, right. So you can see that in the in-order traversal of a binary search tree, you will be getting the elements in some order, that is increasing order. So I can say that in-order traversal of a binary search tree produces a sequenced list. Or if you apply in-order traversal on a tree with numbers, it will print numbers in the increasing order. Here also you can see that in-order traversal on this example produces numbers in the increasing order. Next we will see insertion algorithm. The insert node function adds data to a binary search tree. The function is called insert. To insert data, what we need to do is to follow the branches depending on the rules of binary search tree and insert the new node. And all the insertion takes place at the leaf. So this shows the algorithm for binary search tree insertion. Algorithm is bst_insert. So I can divide this algorithm into two parts. One is the search part, where we will be searching for the element and the place where it should be inserted. This is the search part. So this can work as a searching function. So what it does is, item is the element to be inserted, and ptr is initialized to root of the tree, and I have a variable called flag which is initialized to false. So this searching will be done while ptr not equal to null. In this algorithm, it is assumed that if you are trying to insert an element which is already there in the tree, we will be printing item already exists and it will exit from the function. So but in normal case, if we are trying to insert an element which is equal to some other element in the tree, we will be inserting it in the right subtree. So our rule says that, we can see that the rule says that all items in the right subtree are greater than or equal to the root. So that algorithm described in your textbook is bit different from that. So if item less than ptr dot data, then we need to move to the left. Item is less than. If item is greater than ptr dot data, we need to move to the right child. In both of these cases, we will be keeping track of the previous element in the variable ptr1. So we will be trying ptr1 equal to ptr, then ptr is equal to ptr dot left child. This should be executed while ptr not equal to null. So when ptr not equal to null, it means that we have reached the leaf. In that case, we can get the parent node where it should be inserted from this ptr1 variable. So for that we will be having the ptr1 equal to ptr. So this is the insertion procedure that should be executed if ptr equal to null. So if ptr equal to null, then it means that we reached the leaf. In that case, you need to create a new node, that is new dot data is assigned the item, then left child is null, right child is null. So we will be creating a node with the item. This is the item. Left child is null, right child is null. Then the place where which you need to fix this can be get from ptr1, this ptr1. Then if ptr1 dot data less than item, or if item greater than ptr1 dot data, then you need to place item as right child, else we need to place item as left child. So this is that part which correctly places the new element. So this is the algorithm for binary search tree insertion. We have already said that it consists of two parts, a searching part and an insertion part.